Okay, and let me make sure that the others aren't in the wings somewhere here. Nope, they're not. Um, Now let's talk about how we're going to end the term. I really wish there were more people here before I talked about this. In fact, maybe it would be good just to wait and see if others come in. But here comes somebody now. Houston's here. Okay, so let me get Houston here. So far, odd number students are here. Number 1 and number 3. No one past that though. Houston, can you hear us yet?
Yes, sir.
All right, good deal. Okay, the main reason I'm checking on this is that there have been, I was explaining this to Kira, already this morning, at least 3 or 4 really bizarre computer weird things happening. One in Blackboard, one in email, and one in Zoom. And it was just saying, what is going on? Is this a Monday or something? Okay. I guess the internet ate too much turkey this weekend. I know I did, but that was good. Okay. um, I, I told Kara I was going to start off with how we're going to end the term, but since there's only 2 out of and as soon as I get that out, then somebody else shows up. So now Kyle is here. Okay, we finally got an even person. The top part of the alphabet, 3/4 of them are here. The bottom half of the alphabet, nobody is here. So glad y'all are here though. Kyle, can you hear us yet?
Yes, sir.
Okay, good deal. Welcome. Um, here's the. I'm going to hold off saying how we're going to end the term because I only got 3 out of 8 students here. So we'll hold off on that, but remind me before the end of class to talk about that. Okay. Second thing was, let's see, was something else I was going to mention now, but I don't remember what it is. Oh, I guess this one. I don't know if y'all realize this or not, but this is my last full week of teaching. Okay, teaching. Now, I'll be with you next week too, but not in class. That's final exams week. I'll be grading papers like crazy, and you will be working on your finals probably like crazy. So we'll talk more about that later. But then, so next week is that. The week after that, I've got a couple days to get grades in, and then the month of January, I'll be strictly administrative. They've already got a bunch of things lined up for me to do, and I've got several things lined up I need to do. And then the 1st of February, I'll be retiring. So that will be it for me. So this is my last full week of teaching. Next week, I do teach one class, my second mini-term physical science class. We'll have class on Tuesday, and then their final will be on Thursday. So anyway, this is it for a full week of teaching. But I'm going to miss y'all. I'm going to miss the students. But I'm not going to miss Blackboard. I'm not going to miss Banner. I'm not going to miss some of the administrative part of it, but I will definitely miss the students. So anyway, let's pick up and go from here. We are recording now, and here, as soon as I start to do something, here comes one more. Laurent is here. So the bottom part of the alphabet finally has a representative, and so we got half the class here. I think I'll wait till one more gets in. Now I don't see Laurent showing up, and he hasn't. I heard a pop and he was gone. So
That he left. So
he did.
I guess he came in and then exited.
Yeah. He said something to you, or?
No, I just saw it on the top of the screen that he had left.
Oh, really? Okay. I see. I don't see that. That's bizarre. But anyway, you can't tell if he left for good or you weren't in communication with him. You just saw it. That's
No,
that's strange because I see when they come in, but I don't see when people leave, unless I just happen to catch it. What I'll do, the thing at the bottom, I don't know if you see it or not. It's the toolbar. When someone comes in, it pops up, and I look for them. But then sometimes it'll pop up on its own, and sometimes that means somebody left. But I don't get a message that they left. I just do it. I do get a message when they're coming in. All right. Well, then let's proceed. We almost had half the class here, but we don't anymore, so let's go on. We're in Chapter 12, Vector Valued Functions, in Section 12.3, Velocity and Acceleration, and we're on page 838, near the top of the page, Example 2, under Velocity and Acceleration Vectors. Okay. Example 1 was on the PowerPoint. Example 2 is not, so that's why I'm on the whiteboard here. So let me get my pad and my ionizing pen, and it says, okay, here's some, Laron's back. Good. As soon as I try to get started, someone else comes in, so that's good. I've already got him marked here. All right, Laron, well, he's still connecting. Did you make it in this time? Excellent. Okay. Boy, I got a pop in my ear and then you were gone. So I didn't know what happened. But I got you marked here. All right. We got half the class here. I'm going to wait till at least one more student shows up, and then we'll go over how we're going to end the class. Now, if it turns out that we don't get any more than these 4, remind me before the end of the class to go over how we're going to wrap things up. So we're getting ready to get started in Chapter 12, Vector Value Function, Section 12.3, Velocity and Acceleration, and we're on Example 2, the top of page 838, and we got started on it last time. I think we drew the graph last time. So I'm not going to go back and show the path again, but what we will do is pick up from this, okay? Any questions before we get started? Okay. Here is the function r of t. This is a position vector as a function of t, which when they're talking about velocity and acceleration, you can almost be guaranteed that t stands for time. If you're talking about just some x, y, and z type stuff, not talking about velocity acceleration, just talking about first and second derivatives, it could be that t is just a parameter, has no affiliation with time whatsoever. This is talking about time. Otherwise, velocity and acceleration don't make a lot of sense. Okay, so r of t, position vector, is a function of time, and that is time for this one, is t squared minus 4 in the I direction. This is a planar graph, plus tj, t in the j direction, okay, the y direction you might say. It says find the velocity and acceleration vectors when t is equal to 0 and t is equal to 2. Well, let's just first find what the velocity vector is. The velocity vector is a function of time also, and it's the first derivative of the displacement vector, which someone tells me what that would be. It's pretty easy. Anybody? Take the derivative of the I component. What do you get? Anybody?
T.
2t.
T.
2ti. How about the j component? Derivative of t is 1, just 1. So there's your velocity vector. The acceleration vector, on the other hand, is the first derivative of the velocity vector, which is the second derivative of your displacement vector. And what would that be? I component would be anybody? It would simply be 2I. 0j, because the derivative of a constant is 0. There's your acceleration vector. At any time t, it's always going to be 2 times I. That's it. Okay, that's its acceleration at any point along its path. Okay, now that's not what they're asking for, though. They said find the velocity and acceleration vectors when t is equal to 0. So let's do v when t is equal to 0. And what would that be? When t is equal to 0, the I component would be 0. The j component would still be 1j. So that's it at t equals 0. The acceleration vector at t equals 0 would be what? It's always 2I. No matter what the t is, no matter where you are, it's always 2I. Let's do the velocity vector when t is equal to, I believe the second one was 2. And when t is equal to 2, what would be your velocity vector? T equal to 2 times 2, 4, really high level math today, 4I plus j, constant j component of your velocity vector, always j, that's it. The acceleration when t is equal to 4, at t is equal to 2, would be, again, no matter what the time is, where you are on the curve or anything else, the acceleration vector is always 2I. Okay, let's see if I did it right. The velocity vector is 2ti plus j, got it. Acceleration vector, second derivative of the position vector, 2I. So when t is equal to 0, the velocity vector is just plus j, and the acceleration vector is your good old 2I. And when t is equal to 2, your velocity vector is 4I plus j, and the acceleration vector is still just 2I. Now, they'd show a figure in the book and I'm not quite following why they did this. Okay, I'm trying to figure it out. The figure we did last Wednesday, or Wednesday a week ago, 2 weeks ago. Yeah, no, Wednesday, a week ago. It shows the one we're talking about. And the acceleration vector at every point is 2 in the I direction. And you see that. That's at the top of page 838. Okay? Then beneath that, they show a curve that's almost like it, but they show basically a comet going around the sun. And then they show an acceleration vector always pointing to the sun. And they're saying, oh, but this isn't the same one. And I thought, well, then why did you put it right there? But that's what figure 1213 is, the one we were just doing. For an object moving along a path shown in figure 1213, note that the acceleration vector is constant, has a magnitude of 2, and always points to the right. They only showed 2 points there, but any of the points would work. That implies that the speed of the object is decreasing as the project moves toward the vertex and increasing as it moves away from the vertex. Okay? Now it says, this type of motion is not characteristic of comets. Okay, why would you expect it to be characteristic of comets? Comets follow, just like every other object in the solar system, major object, follows elliptical paths, not parabolic paths. So that's what sort of confused me. They showed the figure as if this had something to do with the problem. It isn't. It doesn't. Okay. The type of motion is not characteristic of comets that travel on parabolic paths through our solar system. No, they don't. They travel in elliptical paths. Okay. For such comets, the acceleration vector always points to the origin, which is the sun, and actually, in terms of astronomical things, that's pointing toward a focus of the ellipse. An ellipse has 2 foci. The sun is always at one, and there's nothing at the other one. Okay, and this comets are going not, and they just happen to draw it at the origin here, but that's not where. So I don't know. I just, it's a mystery to me why they put it in there. Comets do not follow parabolic paths. Okay. And this implies that the comet speed increases as it approaches the vertex of the path, decreases as it moves away. That's certainly true. But those are not parabolic paths. Those are elliptical paths. It's just the other side of the ellipse is so far away, you don't even realize it is a closed circle. But otherwise, comets, once they went in once, they'd never come back again. And Halley's comet, for instance, it comes back about every 70 years. And other comets always come back. Some that we have only seen once, it's just because they got such a long journey to make before they come back again. Or they may get blown apart if they hit something else, like Schumacher-Levy, I think, did when it got a little too close to Jupiter on its path toward the sun and got fried. Okay, but that's, I just was confusing. I've spent too much time on that. Let's move on to example 3. I'm trying to remember where the book picks up, the PowerPoint picks up again. I think it's projectile motion. So yeah, we got example 3 and 4 to do. I think we'll go on and clear this. Does anyone need this any longer? Okay. So here's example 3. And example 3, even though it's not on the PowerPoint, you can go to larsoncalculus.com for an interactive version of this type of example. It says here, sketch the path of an object moving along the space curve C given by this vector r of t. And since they're asking for, well, no, later they'll find the acceleration, velocity and acceleration vectors, which indicates t does stand for time. It could just be a parametric t. This is not. This is ti, plus t3j, t cubed j, plus 3tk. This is a space curve now, not a planar curve like the last one was. And this is good only for t's greater than or equal to 0. Okay, that's the position vector. Says sketch its path. Now this is tough. Okay, I really hate doing this because it's really hard to sketch these paths of the three-dimensional, because I've got a two-dimensional board here that I'm asked to do a three-dimensional sketch on, and that is always hard. Okay, so if this is your x-axis, this is your y-axis, and this is the z-axis, you can arrange them not any way you want to, but any right-handed orientation. That when you put your fingers toward the x-axis, bend them toward the y-axis. The z-axis is where your right thumb is pointing. Okay, this is a right-handed system. Okay, now to sketch it, and t starting at 0, so when t is equal to 0, that would be 0i plus 0j plus 0k. So there it is. That's when t is equal to 0. It's right there at the origin. Okay, now how about when t is equal to 1? That would be 1i plus 1j plus 3k. So if you go 1 unit I, 1 unit j, and 1, 2, 3 units k, you would be somewhere, okay, here is the point on the xy plane, and go up 1, 2, 3 units, somewhere right around there. So it left, get out of there. This is such an aggravating thing. So hard to draw on this when the pencil is so sensitive. So it leaves here and heads up there somewhere, somehow. Okay, let's do t is equal to 2. That would be 2i plus 8j plus 6k. So that would be 2i, and that would be 2, 3, 4, 5, 6, 7, 8j. So, and the xy plane is somewhere over here, and then what did I say? 6 up. 1, 2, 3, 4, 5, 6. So it would leave here. This is a lousy drawing here. Go somewhere. Here and heading on up. So maybe I should have been going up this way. I think that's how I should have been going. Okay, so this first little bit that I did here was ill-advised. Okay, something like that. If we wanted to, we could try a third point when t is equal to 3. It would be 3i plus 27j. Don't think that's going to work. Plus 9k. That would be out. So it's heading up and out rather rapidly, and really in the y direction, going really fast there. Not very much in the x direction, though it's always positive. Z direction is going up 3 times as fast as it goes on the x direction, but the y is taking over. So it's dominated at large value t by this t cubed y. In other words, it sort of swamps everything else. Okay. Now, what it asks for is the velocity vector. Well, the velocity vector, as we said before, is the first derivative of the displacement vector. God, this thing is so aggravating. Okay, and anyone want to hazard a guess what that would be? Anybody? First derivative of t is 1. So it's 1I plus, anyone want to make a guess on this one? Three t squared j plus first derivative of 3t, 3k. My pen's not writing well, so that makes it look really ugly. Okay, now that means here at the origin, where it's beginning, the velocity is 1 unit to the right, out the x-axis. I don't know why I said right. Okay, plus, and 3 units in this direction, so it's heading here, and 3 units upward. So 1 unit to the out the x-axis, 3 units out the y-axis, and 3 units up this. So in the YZ plane, it's 1 to 1, and just a little bit of a push in the x direction. Okay, that's just at one point. Let's do the acceleration vector. If I could get my pen back over here. A of t, which is the first derivative of your velocity vector, which is the second derivative of your position vector, and that would be 0I 6tj, first the derivative of this, 6tj, and this is, if I can read my writing, 3k, which is just a constant. That's all, folks. So the acceleration vector is only in the j direction. Okay, it's just constantly heading 1 unit out each time in the x direction, 3 units out each time in the z direction, but it's taking off and going in the y direction. That's the only component of its velocity that is non-zero. Okay, after a bit. All right. And find the velocity and acceleration vectors when t is equal to 1. So v of 1 would be, well, that's just I. So it's still I. No matter where you are, its velocity vector is 1 in the I direction, plus 3j, because that's 3 times 1 squared is 3 times 1 is 3, and plus 3k. So that is the velocity vector when t is equal to 1. The acceleration vector when t is equal to 1, that's pretty, whoa, why did I put that? Sorry, I rewrote t, and I should have put a 1 there. Okay. And that's supposed to be a 1 also, and this would be 6j. Because when t is equal to 1, that is 6 times 1 is 6j. And that's a rapidly increasing acceleration vector in the y direction only. Constant in the x and the z direction, but rapidly increasing, linear increase in the y direction. Okay, let's see how the book did. Velocity vector was I plus 3t squared j plus 3k. They got that right. The acceleration vector was 6tj. They got that right. And t is equal to 1. Your velocity vector was I plus 3j plus 3k. And the acceleration vector was 6j. And that's all, folks. Okay. Now, so far in this section, you have concentrated on finding velocity acceleration by differentiating the position vector. Many practical applications involve the reverse problem, finding the position vector for a given velocity or acceleration. And that's demonstrated in the next example, which is example 4, which I don't know why they don't have on the PowerPoint, but if I'm just going to go check, but I'm pretty sure I'm right that they go right to projectile motion. Let me make sure. Well, where did my thing go? Okay, I have to go from current slide and advance from example 1 to projectile motion. I was right. Okay. So let's go back to the whiteboard. Okay. Now, I saw something pop up. Still only got 4 students here and nobody waiting. So, all right, excuse me just a minute, folks. Let me fill you in on a little something else in between problems here. Hold on. I think we went over all this earlier, but for those who may not have been here just a little bit, part of this is excuse and part of it is reality. About 6 weeks ago, I had a treatment for the leukemia. My white cell counts had just exploded, 130, 140,000. They're supposed to be 11,000 at the max. Okay, so the doctor, got to have a treatment. And he did, because the counts were so high, he did 10% one day, 90% the second day. The first day I could tell there was a battle royale going on inside. I was hot. I knew it was just tearing up those white cells, and I hoped little else. And then the second day I thought, if that was 10%, what is today going to be like? It was next to nothing. I mean, I could still feel little stuff going on, but it wasn't bad at all. It took longer because it was more drug, but it wasn't bad at all. And then I was supposed to have a second treatment 4 weeks later, 1 month later, because my counts were so high. Well, I knew in my heart of hearts that first day had taken care of the counts, but they don't listen to my heart of hearts. They go by the protocol. But I'll tell you this, before the treatment, when they had done the blood work to find out how high the white counts were, they found out I was also very anemic. But I'm usually anemic after a treatment, but this was before a treatment, but my white cell count so high that was sort of suppressing my red cells. So right before the treatment, like a day or two before, I just had no energy whatsoever. I thought, well, that's the anemia. He was acting like I should be really no stamina. I had no stamina. Well, we had the treatment, and after the treatment, it was even worse. I mean, I could hardly walk upstairs before my heart was just beating like a drum. Even at night, lying in bed, I could hear my pulse. I could hear my heart beating. That wasn't good. I knew my blood pressure was up probably a little bit, and what I figured it was the anemia. And I turned out being right. What I didn't know is how severe the anemia was. But anyway, I went for 4 weeks just exhausted. I could do stuff, but it just wear me out. And when finally it came time for the treatment, usually to do the blood work the day of the treatment, I emailed the Sunday before the treatment on Friday, and I said, can we do the blood work on Wednesday rather than Friday morning when I have the treatment? I didn't get an answer on Monday. I didn't get an answer on Tuesday until something like 5:40 in the afternoon. I finally got an answer. Yeah, it'd be okay to go on and get the blood work done. So I went in early Wednesday morning before I have first class isn't until 10 on Monday and Wednesday. So I went in it, early to get the blood work done. And I did not make it home before there were 3 messages on my machine, my telephone. Of course, I wasn't answering while I was driving. But when I got home, I saw the messages and called back and didn't get the nurse who had been trying to call me, but another nurse read me what she had left, and she said, "You are critically," she said, "the Gazyva did an amazing job on your white cells. Went from 140,000 down to 1.4 thousand, which is way below where the minimum should be. The minimum is 4,000, maximum is 11,000. I was almost a quarter of what I should have been." So yeah, it had done an amazing job on the white cells, but it had also kicked around the red cells, the platelets, and other things that were already low, but not that low. Well, I could have told them the week of the treatment, right before and several days afterwards. I mean, I had zilch energy. Every week after that, I was feeling a little bit better, a little more energetic and stuff, but still not good. And so when they did the blood work, I was critically anemic. And they said, "You've got to go in for a transfusion." Not an infusion, which they had scheduled me for, but a transfusion. So I went in on Friday. This is the week before Thanksgiving, and got the actually it may have been the week before that. I don't remember, but anyway, got the treatment done. The transfusion, and they actually gave me 2 bags of blood. I thought that I was just going to get 1. I got 2, and I mean immediately, even while they were doing it, I was feeling better. And when I get up and go to the restroom or something like that, my heart wasn't pounding and that kind of stuff. So I knew it was coming back. But they had me go. They also, my neutrophils, which are the sort of like the white cells that really fight the diseases, they had also been battered badly by the treatment, so they were probably critically low as well. I don't remember they actually used that term, but I believe they were. So I had to take a round of 4 shots to boost the neutrophils. And anyway, that was over Thanksgiving. So anyway, I feel so much better now, but I'm still somewhat low on energy. And I can tell everything's not back to normal, but I had the blood work done this morning. I went in before 7 o'clock, shortly after the lab opened, so I could get the blood work done. But even then, I had to wait a while. And so I'll find out probably in a day or two whether I have to go in for another transfusion on Friday. But anyway, just to let you know, every now and then I've got to stop and get a little bit of boost of caffeine or something, because I'm not nearly as tired as I was, but I'm still pretty tired. Okay. I think we were getting ready, before I got off onto all that mess, to do example 4. Okay. Here's example 4. An object starts from rest. Okay. Now what does that mean? An object starts from rest. Well, that means it's not moving. Well, movement is indicated by your velocity vector. The velocity vector at time t equals 0, that's starting from rest, would be 0, because it's not moving at the start time. Okay? And it's at the point, and this is a point now, 1, 2, 0. So this is a 3-dimensional problem here. And it moves with an acceleration of, so the acceleration here, at all times t, not just initially, but at all times t, is j plus 2k. That's its acceleration at all times t. Now, an interesting kind of a setup here, even though it starts at position, the k here is 0, it has an acceleration in the k direction. Even though it starts with an initial x component, it has no acceleration in the x direction. Now, does that mean it's not going in the x direction? No, it doesn't. In fact, well, we don't know for sure, but this is the, and here's what I'm going to call this. This is where it is at rest, where it starts from. So this is your position vector at time t equals 0. It's at 1, 2, 0. Velocity vector at time t equals 0 is 0 because it's starting from rest. The acceleration vector at any time is j plus 2k. Okay. And we're dealing in feet and seconds. Okay. So that's your position and your time intervals. Okay. It says find the location. So what we're looking for is r at 2 seconds. This is what we're looking for. Okay. How do we get there? Okay. Now, for those of you, and I know there's in the class there's 3 of you, only 1 here now, who are taking differential equations, you would refer to this as an initial value problem, okay? Because you know a second derivative here, and that's what acceleration is. A second derivative is equal to this, and you know 2 initial conditions. First, your position initially and your velocity initially. And that's a classic setup for an initial value problem. So what we would do here is I would write this way. The a of t is actually d, this is such an aggravating thing, dv dt. Now before I wrote it as v prime, that's a little easier to write, is equal to this. Okay, so I think I'll write this again. J plus 2k. This is so aggravating. Plus 2k. Oops, that's supposed to be a housetop. Okay, what I'm going to do, and this isn't quite legitimate, but well, it is legitimate, but I'm going to write that in differential form. dv is equal to j plus 2k. My writing is so bad on this thing, it just refuses to write sometime. dt, that's written in differential form. Then integrate both sides, okay, and what that gives you is v of t is equal to, I don't know what that line is there. Oh, I know. There's my integral and there's my parentheses. I thought that's a strange looking dude there. Okay, this would be tj, antiderivative of 1 is t, plus 2t k plus some constant vector. So I'm going to write it like this. Okay. Now, let's put in what we know. V of 0 is equal to, no, this isn't V, that's an R. I can't read my, no, it is V, that's V. V of 0 is equal to 0. We know that. That was given right up here. Well, that implies that the C vector had better be C at time t equals 0. Okay, well, let's plug in and see. This gives us 0 plus 0, and this would imply C vector also has to be 0, because if this vector is the 0 vector, now I didn't really write that well, but I guess it's okay, then C has to be 0, because this part is 0, that part 0, and for the I part to be 0, you're okay. All right. Well, what is the velocity vector? This is dr dt. Okay. And since this is 0, I'm just going to ignore it. Okay. So I'm going to do the same thing before, but rather than writing it out, I'm just going to write my dt over here and integrate here and integrate here. And this gives you r as a function of time is equal to antiderivative of t would be t squared over 2, that's in the j direction, plus antiderivative of 2t would be t squared in the k direction, plus some other constant. I'm just going to call it c again, just because I don't want to make up a new letter, plus c. Okay, but when t is equal to 0, this has to be 1, 2, 0. 1, 2, 0. We know that from up here. R of 0 is equal to 0. Well, that implies that this C vector here has to have a component, the I component has to be 1. Gotta be, because there's no I component here, no I component there. It has an I component here, so that's 1. The J component, when t is equal to 0, I guess I ought to write this out. That would be, let me write this out, 0j plus 0k plus c. Okay? So this is going to be it. And that has to be 1, 2, 0. Because the two components here, j and k, are both 0 when t is equal to 0. So therefore, this vector has to be the C vector. All right? So let's write in what that is. That would be I from right here, 1I plus t squared over 2 plus 2 in the j direction plus t squared k, because the constant here is 0. Okay? So there is your position at any time t. You're integrating and using your initial conditions to fill in to calculate what c is. Okay? Now, the question was, what was r of 2? Well, if this is r of t, r of 2 would be I, okay, because there is no velocity and no acceleration in the I direction. Okay, no acceleration, so there's no change of velocity. The initial velocity was 0 there, so it's not changing. So that's going to be I plus, and you plug in a 2 here for t. 2 squared is 4, over 2 is 2, plus 2 is 4j plus 4k. So there is your position vector at time t equal 2. Okay, now let's see how the book did. Well, I'm on the wrong page. R of 2 is I plus 4j plus 4k. Got it. You can go down the way there and see what they do. When you see it says starts from rest, you know right then initial velocity is 0 in every dimension, the I direction, j direction, and k direction. It's 0, and that is a 0 vector. That's what I was thinking I should have there, but I didn't do it. Okay, now and your initial position vector is got to be I plus 2j. They wrote it that way. I didn't write it. Yeah, I did somewhere, I thought. Down here I did, or wherever it was. I left it in just IJK form. Here's an error I see. This should be the vector bracket. See, I'm also teaching linear algebra, and same author in his book, he uses parentheses. I forgot to put that here. Okay, but then here is where we got the acceleration, and that is dv dt. Write that in differential form and then integrate both sides. This gives you v of t is equal to ti plus 2tj plus no tj plus 2tk, and that's your velocity vector, and that is dv dt, dr dt. Write that in differential form. Oh, and your initial velocity is 0, meaning nothing is changing there. So here the plus c that you had here is equal to 0, because when t is equal to 0, that's 0, that's 0, and of course the I component is 0 as well. So you've got just, and that again is the 0 vector. Okay, and then when you rewrite, when you integrate that, t squared over 2 plus t squared plus some constant. Okay, and this is a different constant vector from that one, and you know when t is equal to 0 that this thing has to be 1, 2, 0. Well, this would be 0, 0, 0, so this has to be your c vector here. Now that won't always be the case. If you had some non-zero component here or here when r is equal to 0, you would have to be subtracting, adding, doing whatever it took to get that c vector. In this case, no, it is the constant vector. And then when you plug that in, that gives you I plus t squared plus 2j, t squared over 2 plus 2j plus t squared plus 0k. Okay, and then plugging in r equal 2, I equal, t is equal to 2 here. There is no t there, it just gives you an I. T equal 2 here would be 4 over 2 is 2 plus 2 is 4, j, and then 2 squared is 4k. Alright, and there's your position vector at t equal 2. Now finally we're ready for projectile motion, which is going to be an extension of what we've just been doing. Okay. All right, projectile motion. When you hear projectile motion, what do you think? Anybody?
Like rockets and guns.
That's exactly what I think too. Firing a rocket at somebody or a bullet or something like that, a projectile heading in some direction. And Kyle, you're the one who answered that, right? Do you ever think of that baseball as being a projectile?
Uh, kinda.
Yeah,
Somewhat.
it's exactly what it is. It's just not aerodynamic, and shaped like a bullet or a rocket or something, but it's a projectile, okay? And that's why you can throw curveballs and knuckleballs and things like this and they don't follow regular motion patterns because it's not a very aerodynamic projectile, but it is a projectile motion. And believe it or not, when that projectile, that baseball, leaves the pitcher's hands, it is not coming straight at you. Well, you know that for curveballs and others, but even a fastball, it's following a parabolic path, okay? It's following the path of a projectile. When you hit that baseball over the fence, of course, it's following a parabolic path, okay? Because it's a projectile. And on the surface of the earth, I would say all projectiles follow parabolic paths. Now, I think you said rocket, or I don't know if you said missile or what. Only difference there is
Rocket and bullet.
yeah, rocket and bullet. Okay. Um, Actually, a rocket, if it's a propelling itself, is not a projectile until it runs out of fuel. I mean, it kind of is a projectile, but the thing is, it's not following a parabolic path because it's accelerating itself. Okay. But once that ball leaves the pitcher's hand or the batter's bat or the catcher's hand as he's throwing out the guy at second, of course, or third or first or wherever, it's a projectile and it's following a parabolic path. Now, it's not much of an arc to it, but there is an arc that you probably don't realize, but it's there. Okay? A rocket, of course, could follow a straight line path as long as it's projecting itself. In other words, using fuel and going in a path. But then once it runs out of fuel, then it follows that parabolic path again, okay, from wherever it ended up. So yeah, that's what projectile motion. You now have the machinery to derive the parametric equations for the path of a projectile. Now, here's the assumption. Assume that gravity is the only force acting on the projectile after it is launched. Okay? Now, that's not a safe assumption on the surface of the earth, because on the surface of the earth we always have air resistance. Always have air resistance. But as long as the object is moving relatively slowly, and then the air resistance is negligible. Not zero, but minimal. Okay, you can't ignore it. So that's our assumption here, that gravity is the only force acting on the projectile after it is launched. So the motion occurs in a vertical plane, which can be represented by the XY coordinate system with the origin as the point on the Earth's surface above. Now this would be more like a batter here. Actually, it could be the pitcher as well, but not quite like this. Would be probably the batter, okay? Or if y'all are into other sports like basketball, this could be the free throw line, and here is where the player launches his shot from his height or wherever above his head he releases the ball. That would be the initial height. If this was a batter, that would be somewhere along about 3 feet high, 2.5, 3 feet high. That would be the initial height where he first hits the ball, unless he's really going after a bad pitch, okay, or something like that, okay? But the projectile goes upward and then comes back downward, okay, following pretty close to a parabolic path. Now, I can almost hear Kyle saying, I've seen some pitchers, they're not in an XY coordinate plane. Their ball is going all over. Have you ever caught a knuckleballer, Kyle?
Yes, sir. We have one on the team.
Really?
Yes, sir.
His ball does not go in a planar motion, does it?
No, sir.
He keeps you dancing, doesn't he?
Very much so.
Yeah. And the reason is, like I said, that ball is not aerodynamic. So in that case, there are other forces acting on the ball. If there was a gust of wind, it's going to take the ball somewhere wherever that wind's blowing. And it's not predictable, is it? Probably
No,
not,
sir.
not at all. Okay. So my hat's off to you. You've got a tough job with him. Has he been pretty successful?
Yeah, I mean, when he can locate,
Yes, exactly.
that's when it's good. But otherwise, then we have a little bit of trouble.
Yeah, he has lots and lots of walks, doesn't he?
Yes, sir.
Until he goes to his fastball, which isn't very fast, and then the batter launches all over it. Right. Well, I grew up in the Phil Necro era. You probably don't even remember who he was, but anyway. Okay. Yeah. So anyway, that's why knuckleballs don't follow this pattern exactly. All the others do. Even curveballs, their planes are just sort of sliced or curved in some other direction. Okay. But anyway, that's what we're dealing with. Now, let's take a look at these vectors here. Notice, assume that gravity is the only force acting on the projectile. If it's the only force, then its acceleration is the only acceleration. Okay? The acceleration is down here, down here, down here. That's the only force acting on the ball. Now, sure, when you first hit it, the bat's acting on it. But once it leaves the bat, the only thing acting on that ball is the force due to gravity. And that's always toward the center of the earth. Okay? Now, if this was the pitcher's hand, that's still true. The only force acting once it leaves his hand is the downward force. Now, sure, a curveball, a slider, or some of those other pitches that have some weird spin to them, they can curve in a different direction because, again, the threading of the ball or whatever it is making the air resistant move their pattern. And then, of course, the knuckleball, it's going wherever it wants to go. Okay. Now, notice here the initial velocity is given this way. Now, that initial velocity, if they had broken that into a horizontal component in this way and a vertical component that way, you'll see a couple things happen. Number one, the horizontal component never changes, ever changes. Horizontal component is also constant. That's the horizontal component of the velocity. The vertical component, though, is changing constantly. Here's the vertical component here. Here's the vertical component just before it reaches the peak. It's pretty short there, okay? At the peak, it's 0. Then coming down, the vertical component of velocity is down here. It's always changing because the only thing changing it is the acceleration, which is strictly vertical. If you have no acceleration in the horizontal direction, the horizontal velocity stays the same. If you have acceleration in the vertical component, then it's decreasing the vertical component here, it's decreasing the vertical component here, it's actually making more negative the vertical component here. So yeah, that's the situation. That's projectile motion, parabolic motion. For a projectile of mass m, And the force due to gravity, now this isn't quite right. Oh yeah, no, this is right. I misread it. The force due to gravity is F, a vector force, is equal to M minus mgj. Okay? For a projectile of mass m, the force due to gravity is always downward, and the magnitude of it is mg, that's the mass of the object, times the acceleration due to gravity, and the mass times acceleration gives you the force. The minus sign means it's always toward the center of the earth in the j direction. There is no net force in the horizontal direction, or let me call it lateral direction, or let's see. Yeah, if we're dealing with a plane, it's the xy is all. We're not dealing with x, y, and z. Okay. Where the acceleration due to gravity is 32 feet per second per second. It's often written this way, if I can find my pen here. For those who have had physics, you'll be used to seeing this. If I can get my pen to show up somewhere, there it is. This would be 32 feet per second squared. That's the shorthand for this. You could write it as 32 feet per second, but the shorthand is feet per second squared. In the metric system, the SI system, that would be 9.8 meters per second squared, or 9.8 meters per second. Okay, those are accelerations. Meters per second or feet per second, that's a velocity. Meters per second squared or feet per second squared, that would be an acceleration. Now, by Newton's second law of motion, that same force produces an acceleration, A, where A is your, wherever my pen is here, where is it? Can anyone see where there it is, it's right there. Okay. A is some function of time, and that's what we saw was always pointing downward. So that satisfies the equation. That force minus mg j is equal to ma. That is your net force acting on it, period. Okay, but we saw already that A was strictly pointing downward in the negative j direction. So that means that, just compare this expression to that expression, the m's go out. A is equal to minus j. Okay, minus gj, I'm sorry, minus gj. Consequently, the acceleration for a projectile is given by ma, that's this form, is equal to minus mgj in that form, and that you can divide out the m's, and you have your acceleration of the object is minus gj. So that's the coefficient of your acceleration vector in the vertical direction. Okay, minus gj. Now, and that basically is what this is showing. This is minus gj. This is minus gj. It's a constant, minus gj, not ever changing. Okay, now they jump right into example 5. How are we doing on time? My watch is under, I think it's already, I was recharging it. Okay. All right. We have, oh, here comes Esther. Good deal. Let me get Esther marked present, and then I think we will take a little time out here. Okay, the first half of the alphabet is now perfect attendance, and poor old Laurent is in there holding down the bottom half of the alphabet all by himself. Sorry about that, but you can handle it. Okay. Esther, can you hear me yet?
Yeah.
Okay, good deal. Um, I had wanted to wait until at least more than half the class was here before we went into our end of the term activities. I hope you realize this is the last week of class. We have class today, we have class Wednesday. On Wednesday, sometime, I will post the final exam. And you have until the next week to get it into me. Okay? Now, what I'm guessing the final exam will be, especially with the we've made progress today, but it's been a bit too slow. We're in 12.3 now. Hopefully we'll finish 12.3 maybe in the next few minutes and then move into 12.4. 12.4 is a pretty long section. Okay, so we're not going to make a huge progress on it this time. On Wednesday, we may not even be able to finish it. I regret that. I wish we would have time to get into 12.5. But 12.5 is also a very long section. Okay, so what this is getting down to, oh wait, here comes James. Boy, they're coming in now. Okay. Lauren, you got some help holding down the bottom part of the alphabet now. You and James are there. We're still missing Jemanuel and Jesus. Okay. The J's were a bit slow coming in today, but they're getting here. Okay. At least one is. Okay. So, wherever we end on Wednesday, that's as far as your final will go. Now here's my guess of what's going to happen with that. I've got a test made out for chapter 12, but it doesn't look like we're quite going to finish chapter 12. So what I may give you is a test and say, okay, do the first 9 problems, but the 10th one is optional. Or do the first 8 and the last 2 are optional, or something. We'll determine that on Wednesday. Okay? Now, I should have backed up and said something before I got into the final. And that being that your research paper is due by Wednesday. Okay? Not Thursday, not Friday, not next week. By Wednesday. Now, we'll accept it any time on Wednesday. I'd rather have it by class time on Wednesday. But if it's postmarked or dated on the email or on the message or wherever it is, if it comes in anytime Wednesday, that's up to 12:59 Wednesday evening, 12:59 p.m. 11:59 p.m. You'll get credit for it as being in on Wednesday. Okay, if it's Thursday, you start losing points. So please get your research papers in by Wednesday. Now, your other yes. Absolutely. You've already turned yours in. You've got the bonus points already. I don't know if I've got the grade on Blackboard yet. I know I've graded. I know you've in 3 of my classes. I've graded at least 1 or 2, maybe all 3 of yours. I don't remember. I may not have the grades posted on Blackboard yet. I was explaining to the others earlier. And I don't guess y'all realize this because it all happened. Well, some of it was happening before y'all left, but I had, back in October when I had treatment for my high white cell counts, the treatment was incredibly effective on the white cells, but also wiped out a bunch of reds and platelets and neutrophils and lots of other things. So I had to have a transfusion the Friday before Thanksgiving. And I thought it was going to be 1 bag of blood. It was 2 bags of blood. Of course, I felt really good ever since then, but I can still tell I'm tired. So I know I'm still anemic. I'm not, but I didn't know at the time I was critically anemic. I mean, I had the doctors and nurses just going crazy trying to schedule me to get the transfusion in. I could have told them I was really tired, but I didn't know how badly it was, how bad it was. But it was critical. So anyway, I'm behind on the grading and really far behind on on entering things on Blackboard. I'm trying like crazy this week to get that caught up, but it'll probably be next week during finals when I'm finally not teaching 7 classes that I'll be able to finally get some catching up done. I thought I'd have more time over the weekend, but we had a packed jam full weekend. I never anticipated that much that was going to be going on this weekend. So I am behind. I'll try to get those out there as soon as I can. Okay, so anyway, get your research papers in by Wednesday. And I would love it if you get all your other tests in by Wednesday. Now, most of you, I think, have turned in most of the tests. I can't say that for everybody. I, as I was telling others this morning, I was trying to check emails and the email went out. I was trying to do Blackboard work this morning. Blackboard went out. Completely separate issues here. It's just been a weird ether day. I mean, it's just nothing has been working right, it seems like. And I had a student this morning in the morning class. He couldn't get his sound to work. I mean, it's just all sorts of weird things are happening. So anyway, I'm going to try my best to get everything caught up as soon as I can. Please, you get everything you can caught up as soon as you can, because Wednesday, when I give you that test, I'd like for all your other work to be in already, so you don't have to focus on that and have two things out at once. Because this last test, this chapter 12 test, however far we get in it, that is a required score. That's not something you can drop. That's counting as your final exam. So please, folks, get the other things in today, tomorrow, or sometime Wednesday. So you can only have to focus on that for Wednesday, after Wednesday. Okay, then you get me your finals in as soon as you can. Now here's another issue. Some of you are graduating this term, aren't you? I know at least one is. Yeah. So those who are, I think I have to have your grades in even earlier than everybody else's. I don't remember the exact date now, but please, if you're graduating, get them in just as soon as possible, which means get the other stuff out of the way before Wednesday. For you graduating students, be sure you get everything else completed before Wednesday, so all you have to work on is the final exam. Okay? Because I don't know when I have to have your... What's that? Yeah, I know, and I've got some of them. Some of them are graded. Some of them I've started grading but haven't finished. It's just, like I said, this has been the roughest term health-wise I think I've ever had. Well, I don't want to say ever had. Back when I had the chemo treatment for my leukemia, that was back in about '09 or so. There was a rough term in there too. I tried to have it done as late in the term as possible, so most of the term was okay, but it was a pretty rough fall term that time too. So, but this thing with the anemia, that really, I wasn't expecting this by any means, and it's been pretty rough. But I'm going to try to get caught up as I can. So, yeah. So if you've turned things in and I've acknowledged that I received it, I've got it, I'll grade it, it'll get out there. And some of them, like I say, are already graded. I just haven't had a chance to put them on Blackboard yet. But I'm going to be working as hard as I can this week, and then certainly next week getting all that stuff done. Okay, so that's how we're going to wrap up the term. The other thing is, in wrapping up the term, please do the student course evaluations. They finally got them out there. They didn't get them out there in time for first mini-term courses. They didn't get them out there until last week sometime, and y'all were all gone. So, or not necessarily checking emails and stuff. But they're out there now. Has anyone seen them already? student course evaluations? Anybody? Look for them. Check your emails, your Lawson emails. I think you probably have to use your new email accounts. I think those are the A number accounts. Check your emails and see where those are. It's the same, what is it called, smart evals that we used before. They just had a lot of difficulty getting that to work with this new banner system. But I think they've gotten it done now. Please do the pseudo course evaluations. Okay? Now, let's get back to example 5, where for those who just came in, we're on chapter 12, vector valued functions, 12.3, velocity and acceleration, and we're on page 840, example 5. A projectile of mass, I just spent way too much time talking about stuff. A projectile of mass m is launched from an initial position vector r0. That's what this is, okay? With an initial velocity vector v0. Find its position vector as a function of time. Now, not a single number in the problem, okay? Find its position vector as a function of time. Okay. Now, when it says a projectile is launched, we're assuming that we're in the Earth's gravitational field, which makes that assumption that your acceleration vector is equal to what we just did on the last page, minus, and you take a look at this, minus gj. Okay, we're only in the XY plane here. We're not doing 3 dimensions. We're only doing 2, and that's what we've got. That came exactly from here. A is equal to, wherever it is, there it is. A is equal to minus gj. Okay, so that's where we're starting from. Okay, initial position r0, initial velocity v0. They don't give us any numbers, just that. Find the position vector as a function of time. So we start with this, which is dv dt. That's what A is. And that's equal to minus gj. Okay? Then write this in differential form. Put the dt over here. Integrate both sides. The g is a constant, the minus a constant, pull it out, and this gives your velocity vector here is equal to minus g, and this has a coefficient of 1, the antiderivative of 1 is t, minus t j, okay, plus some constant vector, okay. Now, at time t equals 0, that's what this means, initial velocity, this is v of 0. The velocity vector time t equals 0 is equal to v0. That's what that means, okay? So when t is equal to 0, then your this part is 0, and that means that this c here is v0. Now that won't always be the case. If you had some number in here that was contributing something, then you'd have to make sure the whole thing adds a 0. But since this becomes 0 when t is equal to 0, then this is your velocity vector. So v at any time t is equal to minus g t j plus v0. That's it. Okay, there's your velocity vector. These are all constants. v0 constant, no t dependence in it, just a constant. Okay, now write this as dr dt. That's what velocity is. Rewrite that as this, okay? Then integrate both sides, integrate this, and you have r as a function of t is equal to minus gt squared over 2 plus, now this is a little harder to do, v0, which is a constant now, times t, okay, plus some other constant. Let's just call that c. Well, when t is equal to 0, this is equal to 0, that's equal to 0, this c here must be r sub 0, okay, because that's equal to 0, that's equal to 0 when t is equal to 0, so this must be r of 0 is equal to r at time t. The position vector at time 0 is equal to r0. I mean, it's r of 0 is equal to r0. It sounds like you're saying the same thing. So what is your position vector as a function of time? I wish I had more room. I'll write it here if I can. R as a function of time is equal to minus 1/2 gt squared, okay, and that's in the j direction. I forgot to write that in here. J plus v0 t plus r0. Now, that's a little misleading because if you realize this v0 here could have x and y components in it, so this could be some numbers in here. You'd have to include those here too, okay, with the j. And the r0 could have some values for x and y as well. So you could have your j component is going to have square components, it could have a linear component, and it could have a constant component. Your I component is only going to be an IT here, I mean a VXT here, and a V0 and a RX here. So it would be just a linear component. But that's all we know. We don't have any numbers to go by, so that's what we've got. Let's see how the book did it. Well, we'll see in just a moment. Let's see what we've got here. Oh, there it is. Negative 1/2 gt squared j plus t0 v tv0. I put v0t plus r0. Yep, that's it. So let's watch how they did it. Let me erase my scratch here, and we'll see how they did it. Begin with the acceleration vector. A of t is equal to minus gj, which is just what we used before, right there. Okay. Integrate twice. The first integration, v of t is equal to integral of a of t dt. That's integral of minus gj dt, which would be minus gtj plus some constant. Okay, but okay, why in the world they're doing it this way, I don't know. The good thing to do is go on and evaluate when t is equal to 0. You get v0, so put t equals 0 here, and then the v0 here becomes your c1. So from now on, call that v0. Then r of t is the integral of this one, which is minus g of t minus gtj plus what we just called v0 dt. Integrate that, you get minus 1/2 gt squared j plus c1t, which was our v0t, plus c2, and when t is equal to 0 here and there, then this r of 0 is equal to R0, R sub 0. Okay? Now it says you use the initial conditions V of 0 equal V0 and R of 0 is equal R0. Solve for the constants C1 and C2. If you had done that all along, you wouldn't have both of them to deal with. By doing that, produces C1 is equal to V0 and C2 is equal to R0. Yeah. Okay? Therefore, the position vector R of t is equal to minus 1/2 gt squared j plus t v0. I'll call that v0t, but they do it that way. Well, I guess they put the function in front, so t v0 plus r0. Now, understand, this v0 can have x, y, and z, or x and y components here, I and j components here, so the I component would be by itself, just that times t, but the j component would be then added to this j component, okay? And then this R of 0 could also have I and j components, so this I component here times t plus this I component is your overall I component, and this j component plus the j component t here plus the j component here, that would be your j component, total j component. Okay. In many projectile problems, the constants R0 and V0 are not given explicitly. They're only given, I guess you'd say, implicitly or whatever, maybe with initial speed or initial height. That's what they're getting at here. Often you're given the initial height h, that would be your R0. Would be just that vertical distance h, okay? And your initial speed v0 would be given like this, and then you have to take, if you're given the ij components of them, you know that the vertical component is the hypotenuse times the tangent of that angle, and the horizontal component is the hypotenuse times the let's see, let me say that right, cosine of this. This is the sine, that's the cosine, sorry, which the angle is launched. So often you'll be given just the h, initial speed, angle theta, which it's launched, okay? And the y component will be the okay, it depends on what's given. If your initial speed's given, the y over that initial speed is the tangent of this angle, and the, no, I'm sorry, is the y over, no, that would be the sine of that thing, sine theta, and this would be the cosine theta. Okay. Sorry, I had it right and got myself confused. From the initial height, you can deduce that R0 is equal to hj, because that's only in the j direction, because the speed gives the magnitude of the initial velocity. It follows that v0 is equal to the magnitude of v0, and you can write v0 is equal to x I plus yj, which is, boy, they go through all sorts of weird ways to do this. That's the magnitude of your device. In other words, your hypotenuse times the cosine of theta I plus the speed or the magnitude of that velocity vector, which is the hypotenuse, times the sine theta j. Okay? And that gives you v0, which is the magnitude of that, in other words, the speed of that projectile when it leaves the bat or whatever, times the cosine theta, the angle at which you hit it, I plus v0 sine theta j. Okay. So the position vector can be written in this form. R of t is equal to 1/2 gt squared j plus t v0 plus r0. Now that's that problem we just did, example 5, wasn't it? How are we doing on time? Oh man, we just ran over. Yuck. Okay, sorry about that, folks. Where are we? Right at the bottom of the page here. We'll start right there with the bottom of page 840 next time, and we should be able to finish that page, top of the next page, and the last example, and we'll be through with 12.3. Homework exercises here would be any of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. Any of the odds 11 through 19, they're all at Calc Chat. 15's at Calc View. Any of the odds 21 through 25, they're all at Calc Chat. 21's at Calc View. Any of the odds 27, well, get started on some of these. You may not be able to do them all. Just stop right where we were. Stop at 25. We will pick up and do the rest of these next time. Okay? Any questions? All right. Then we will see you on Wednesday. Get those research papers done. Get those student course evaluations done. Get your earlier tests completed and into me. And then Wednesday, sometime at the end of the day, probably after 4 o'clock, hopefully before 6 o'clock, I'll try to have your final exams out there for you. Now, let me talk about that. There is a tab in this new Blackboard template that they came out with that says something like final exams or midterms and finals or something like that. If I can, I'm going to post it in that. Okay? If I can't post it there, then under week 6, there is something called week 16, a week 16 assessment. That's where I'll post it, if I can. If I can't get it in either one of those places, then I will put it under Blackboard Messages. And whether I get it under the final exam tab itself, and if I can't get it there and I do get it under the week 16 assessment test tab, no matter where I put it under those two, I will put it under your Blackboard Messages. I'll send it out that way, whether I can get it in the other two or not. So you'll have it either just in Blackboard Message or in Blackboard Message and either the final exam tab. If I can get it there, then I won't mess at all with the week 16 tab. But if I can't get it in final exam tab, I'll try to put it in week 16. If I can't get it in either one, it'll always be back there under Messages. Okay? And so it'll always be under Messages, and it may be in one of the other two places, but not both. Just one of those two places and Messages. Okay? Any questions? All right, folks. Get everything caught up. I'm going to try to get everything caught up, though I've got probably a lot deeper hole to dig out of than you do. But I'm going to stop sharing now. Are there any further questions? I've already lost a few people. Any questions? All right. Take care, folks. We'll see you on Wednesday, and we'll be wrapping this baby up. Okay? Take care. Bye-bye.